Yani valla aslında tehlikelerinden falan bahsediyor. Biraz da yakaladım. Havalı bir şey. Yok, hayır, daha önce Avrupa'da deneyimlerim o yüzden. Senin üzerine Alışına mı oturuyorsun hocam?
Hocam nasılsınız? Hoş geldiniz. Durum aslında bağlanıyor olmamız lazım. Ben sizin okulda da bağlıyorum. Bağlanıyorum. Misafir telefon soruyor hocam. Yani ben telefonda aslında destek verdim ama şu anda buna bağlıyorum. Telefon bağlayıp kendisine. En kötü örnek var. Yakmaz hocam. 5 dakika için yakmaz. Açık bırakmamız nasıl diyoruz?
Evet, tabii bakmak falan yapacağız. Her şeyde var. 30 güzel muhteşem. İçi öyle onlarla ilgili birkaç kısmı var. Nerede olacak?
Hocam bu telefon bağlı da görmeyin. Onunla internete düşüyor. Evet. Tamam, şu anda iyi bu. Böyle basacağız. Sen de geçeceğim. Ne yapıyorsun?
Okay, hello everyone. So it's my great pleasure to introduce Ferda, who was my PhD advisor as well back in days. I checked yesterday, it's been 20 years almost since we met first time. There's no need to introduce you, I guess. So I'll just say Ferda from Georgia Tech, and we'll talk about the limits.
Teşekkürler. Herkese merhabalar. Çok teşekkürler davet için. Boulder really was my first PhD student. I was teaching a summer lecture at Sabancı University, and he came with a data set that he analyzed overnight, and he said, "Can we start working on this together?" And I was like, "Okay, let's do that." So that was really more than 20 years ago. It's wonderful to see all of you here, and Istanbul University's astronomy program as well as program in the sciences. I have dedicated my own career to astrophysics, and in particular, understanding the properties of black holes and their close cousins, neutron stars, and understanding how they form, what their properties are in terms of gravitational fields, magnetic fields, and their environments. So, right around the time, maybe a few years before Tolga and I met, I was also starting to think about whether we can take images of black holes with telescopes and whether we can use those images to understand what black hole environments look like. And that has been a long journey. You have probably seen already these images, this from the M87 galaxy central black hole, and this from the black hole at the center of our own galaxy, we call Sagittarius A star, the center of Milky Way. So I want to tell you a little bit about this journey and how we designed the experiment, what were the theoretical foundations of what we expected to see, and what we ended up finding. Let me just motivate a little bit. As you know, the universe is extremely rich. The night sky is extremely rich. There are galaxies, stars, explosions, new planets that we're finding. Why are we studying black holes in particular among so many options that the night sky offers us? Well, one of the reasons is black holes are everywhere and they are extremely powerful. They actually have a big impact on how the universe evolves as a whole. You might think they are small objects. They don't have a huge influence outside of their gravitational radii. But the reality is there is so much energy input and output from a black hole that they end up playing a huge role in how entire galaxies form. And with the James Webb Space Telescope, JWST, in the past couple of years, we're finding black holes that are born and grown very early on in the universe. Just a few hundred million years into the age of the universe, we're finding big black holes that have grown to billion solar masses. So they are, this is the, just to visualize, this is the scale of the galaxy. It's 100 kiloparsecs about across. Where the black hole gets its gas to grow from stars and nearby clouds is about 100 parsecs, 1,000 times smaller than that. Black hole accretion disk, where gas loses angular momentum and slowly makes its way down to the black hole and becomes part of it. And in the meantime, gives out radiation that we can detect with our telescopes, is about 0.1 of a parsec, another few orders of magnitude. And then the innermost region that defines what a black hole is even smaller than that by a few orders of magnitude. We're now down to 10 to the minus 4 parsecs for a typical black hole size. Okay, and this is what we wanted to reach with our telescopes in order to see that there is really a region where outside of which there is light and inside is dark. That would be the telltale sign, the signature of a black hole. That light comes in, matter comes in, but it crosses a region from which there is no light emission, and we wanted to see the signature, okay? And then even smaller scales, all our theoretical efforts, all our computational models are focused on understanding how this gas moves around the black hole and how it heats up and cools down. It's a plasma because it's a very hot gas. So it's completely ionized into typically hydrogen, helium, and electrons. So in this turbulent plasma, how is energy going in and coming out? How is it being radiated? And that forces us to think about length scales that are 10 to the minus 11 parsecs. So by now, you can see we are 13 orders of magnitude below the scale that we are interested in. So a lot of my work with my PhD students and our collaborators are focused on trying to understand this scale and this scale in order to resolve those scales.
Wait, this black hole, why always it comes to on the face, while maybe a little bit I mean, both pictures are just, yeah, they are first. But some of them should be implied and we should keep it from sight.
That's a very good question. Why does the image look like this? And I am going to get to that. We are not seeing it at a special angle. It is a special type of accretion flow. It's not a disk. It's not like interstellar makes us think that it's like some thin disk and you can see it this way or this way. It's not like that. The types of black holes that are near us, like Sagittarius A star, like M87, like many others in our neighborhood, are actually a different type of flow where it's more spherical. So it's more of a torus. I'm going to get to that. So whether you look at it this way or this way, because of the way light bends around the black hole, it always leaves this dome with simit around it. Okay, so it's not a special viewing, John.
Wherever we look, we will see the same.
More or less. There are small differences. Because you're astronomy students mostly, let's also, I mean, I'm not an observer, Tolga is, he can find his way around the sky, and many of our hojas here can actually find their way around the sky. But let's orient ourselves. This is one of the sources that we looked at. This is the M87 galaxy in the Virgo cluster. And why did we want to study this object? Well, we knew that there was a powerful jet about the scale of the galaxy that is, that we've known for about 100 years. So we knew there's a very powerful source at the nucleus. And this is how we find black holes in general. We find, even though the black hole itself doesn't radiate, as matter falls in, there's a lot of heat being generated, which turns into radiation. So this is how we targeted M87. But let's go back to why black holes have that very particular shape in their images, and go back to the basics of what a black hole is in order to understand. So early work about how light behaves around a black hole dates back to the 70s. There's a Vardy, 1973. There's another early accretion flow paper by Luminet in 1979. The idea is that if this is the black hole right here, and we went and stood with a flashlight behind it, the only thing that you would see is this part, that is the photon ring being lit up. Interior would be darkness, and you would not see much around it. Why is there this very bright ring around it? That comes back to what general relativity tells us about black holes. So this is a Schwarzschild black hole as an example, which is a particular non-spinning black hole. And here I'm marking a few, actually I could just use this, a few special radii. This is the photon orbit. This is the most important characteristic, even though we keep talking about the event horizon. This is actually, it turns out to be a more important characteristic. For a Schwarzschild black hole, it's at 3 gravitational radii. The horizon itself, that point of no return, when you enter, you can't come back out, is actually at 2 gravitational radii. So let's say that, let's generalize this concept and shoot a bunch of rays from any direction towards this black hole and see what happens to these rays. Okay? So let me try this. What do you see? This is 10 gravitational radii. Each one of these rays, even the one that's coming at 10 gravitational radii, as you can see, its trajectory is being bent by the gravitational field of the black. Okay? But if it's within 5 gravitational radii, as an observer sees it, as somebody distant sees it, not only is the trajectory bent, but it ends up inside this, inside the black hole. So that's the part that leaves absolutely no light coming out, okay? But there is also a special radius, as I mentioned, which is this photon ring, where I think I have another slide showing that. So that leaves that shadow of a predicted size for the black hole. You can give me the mass of the black hole, and I can tell you exactly how big that hole should be. But we can do one more thing, which is actually, yeah, I'm going to go back here. There's a special radius, as I said, where if you put a ray of light tangentially in orbit around it, it would keep on circling more and more and more and picking up, like becoming brighter and brighter. So in the image, that cement part that we're seeing really is primarily those rays of light that have made multiple circles around the black hole. So whether you look at it this way or this way or this way, as long as that light has had a chance to go around multiple times in that sphere, you're going to see it as a bright ring. That's why it doesn't rely on a special geometry. It just relies on a special type of black hole. Okay. So I showed you those ranges of scales from the galaxy all the way down to the plasma. Our tools for simulating these, like writing down the physical equations and trying to understand what happens to this gas and how much light we can see from it, relies on typically something called a GRMHD simulation. I don't like acronyms too much, but I'm going to introduce this one because we use it so much. This is general relativistic magneto-hydrodynamic set of equations. So there's hydro, which is the gas. There's magneto, which is the magnetic fields tangled with the plasma. And it's general relativistic because we put it in the space-time that is appropriate for the black hole and solve the equations in that setting. This is a recent simulation with my postdoc Mark Avara. And what happens is that we typically put the gas somewhere far out, just as a reservoir. And from that reservoir, we let it evolve according to these equations. And as you can see, an accretion flow forms, and this is the inner boundary of the black hole. So we start from these initial conditions, let that reservoir of gas come in, and then we look at what this accretion flow does. Why is this useful? Well, we can explore a lot of different physical properties and convert that into, if I turn the telescope, what would I observe? Okay, connect the physical properties to observables. For example, we don't know if the black hole is spinning and how much. We don't a priori know how much gas is falling onto the black hole, which we call a mass accretion rate. We don't exactly know how particles are heated and therefore how they're radiating. So we simulate that under many different conditions. So this is a way to explore the parameter space of all of the physical conditions we're interested in. We then have to, as I said, connect physical characteristics to observables. First, you do those general relativistic magneto-hydrodynamics equations, but you still have to figure out what an observer or a telescope sees. And that part is called general relativistic ray tracing or radiative transfer. You take each one of those simulation volumes, like this one, like this one. So this is some gas flowing out, this is gas flowing in, its density, temperature, magnetic field, and then you trace these rays, just like the ones that I have shown you with that initial black hole, to a telescope. Let's say this is the screen of a telescope, and then we figure out, okay, what would this look like? We've done this both in our group and as a collaboration with the Event Horizon Telescope group. And we made a simulation library. We said, let's change everything we can think of for black holes that look like the ones nearby. And this is what we saw. Okay, changing black hole spin, observer inclination, electron temperature, black hole spin, that maybe I said that already, mass accretion rate, everything that you can think of, and solve those physics equations to see what would the image look like. Okay? And this is the gallery. It's like a postcard, like a stamp collection. But each one of these simulations are many, many hours on a supercomputer. So it's a bit of an intensive stamp collection, but it's okay. So what do you see? Well, all of them have this ring, right? But some of them are thicker, some of them are thinner, all of them have the hole, all of them have the ring. And one other difference in the stamp collection is that some are full circles and some are hilal, right? Crescents, like about half a circle. What is that about? Well, that's where our viewing angle matters. If you're looking at it even though it's a torus, it's spinning around the black hole. If you're looking at it closer to the equator, then the gas is swirling towards you and away from you. And that introduces a Doppler shift. And when you introduce a Doppler shift, it means one side becomes brighter than the other. Okay? So the Doppler effect leaves crescent-looking images like these ones. If you're not at the equator, but you're looking at it from another angle, this effect is reduced. So all of those are these more symmetric images. Any questions so far? I can stop and take questions.
The angular momentum of the torus, does it have any effect? I mean, is it for a near here?
Is the angular momentum of the, well, basically all gas starts out at some large radius, and even a small velocity at that radius, you know, will cause it to have an angular momentum. What we typically see is a Keplerian profile. And when there is magnetic pressure building up, we see a sub-Keplerian profile, so a little bit shallower than that. But more or less, accretion flows settle into Keplerian profiles.
Which parameters did you change to get this full gallery?
Everything you can think of, pretty much. Observer's inclination has an observable parameter. Black hole spin, mass accretion rate, magnetic field morphology, like how we started out the magnetic field in those initial conditions. We changed, I don't know, electron temperature. So everything that you can, I mean, this is a subset. We ran quite literally several hundred thousand images.
And then I will ask in Turkish, then
Yeah.
you can answer.
Yeah.
Bu işleri yaparken karanlık enerji ve karanlık maddeyle ilgili parametrelerle ilgili herhangi bir şey koyuyor musunuz? Yani nasıl?
Do we take into account dark matter or dark energy parameters? Luckily, at the sizes where the gravitational field of the black hole is dominant, we don't have to worry about dark matter or dark energy. Further, these are centers of galaxies where it's dark matter to begin with, and at this scale, close to the horizon, we don't have to worry.
In the simulations, do you follow real particles? Is it a real class of simulation?
That's a very good question. So there are two ways to do plasma simulations. The one that I'm describing right now is treating the plasma as a fluid. That's why I said magnetohydrodynamics. It's like average characteristics of the plasma and the magnetic field. But another way to do it, especially if your density is low, is take individual particles. Here's an electron, here's a proton, and actually follow them around. These are called particle in cell simulations. My group does a lot of particle in cell. Everything that I'm showing you here is hydro, so an HD. And why is this important? Because even though it gives us a very good idea of the general characteristics of a black hole accretion flow, it can't tell us exactly what's happening to the individual particles in HD simulations. And sometimes that's where exciting things happen, like electrons get a lot of energy and shine, or zip around, or cause what we call a flare. And for those, we turn to particle simulations.
You use positrons and
We do.
in the particles.
We do actually real mass ratio. So we are able to do not a pair plasma, but a real proton, electron, 1836 mass ratio. Okay. So I said, it doesn't matter what direction you look at the black hole, give or take, but it matters what type of black hole you look at. And it also matters what wavelength of light you carry out your observations. The reason is that we talked about this swirling hot torus. And if you look at it at a long wavelength, like 1 centimeter of light in radio, this is what it would look like. As you can see, it's nothing like that simulation gallery that I showed you. There is no hole at the center, there is no bright ring, nothing is happening, right? So like, if you looked at this, you wouldn't be able to see the heart of the black hole and its physical properties. This dates that, so this simulation that I'm going to show you is a more sophisticated version of the work that I did back in year 1999, 2000, that basically chose the wavelength at which we should be doing this event horizon telescope experiment. The reason is, even though this gas is opaque at 1 centimeter, as you can see, if I now change it and bring it down to 1 millimeter, the amount of light that's emitted is going to go down, and it's going to come closer. And let me do that one more time. You see this opaqueness is going to disappear. You're going to start seeing the heart of it right around 1 millimeter. Okay, so there it is. So we said for nearby black holes, this is the work that we did in year 2000 and 2001. Nearby black holes, let's identify which ones we might be able to see with telescopes, and identify the wavelength at which that opaqueness disappears. So here, as you can see the image, this is the image size on the y-axis. This is the frequency at which you're making the observation on the x-axis. And it shrinks down and it hits about the Schwarzschild radius at a millimeter. So we said we can have 2 targets, Sagittarius A star and M87, which are big enough in the sky so our telescopes can resolve it. And we should do it either in the X-rays. This was at the time a space X-ray interferometer concept called Maxim, or we should do it at a millimeter if we're doing Earth-based. And there were already some efforts to use a technique called interferometry. This is Lowe and collaborators in '98, and Thomas Kutzbaum and collaborators at the same time. As you can see, they were already getting measurements of the sizes of the black hole at these longer wavelengths. And he said, what we need to do is build the experiment. And we started, we became founders of the Event Horizon Telescope collaboration that turned the experiment into imaging at 1 millimeter. Now, when I say identified Sagittarius A star and M87, which we ended up observing, and those were our ideal targets, they are still extremely small objects, extremely small. And for astronomers in the audience, what I mean by that is 50 microarc seconds is what you're trying to resolve, or millionth of a degree. Okay, the moon is half a degree. So we're talking about a million of that. So what telescope can do this? Like not even James Webb, not even its predecessor Hubble, nothing can reach that kind of resolution. So we need to do another technique. And I'm going to introduce that to you because it was an important part of how we obtained the images. So this is the Event Horizon Telescope array as it was in 2018. We added more dishes to the array since then. As you can see, there are telescopes that can observe at 1 millimeter of light at different locations around the Earth. Okay, This is Hawaii, this is Arizona, where I used to be, Greenland, practically at the North Pole, exactly at the South Pole, the South Telescope. This is in Chile. So these are all dishes that can observe at a millimeter wavelength of light. And the technique is that, let's say 2 telescopes that are in different parts of the world. And let's look at our source at the same time and record the signals coming in. There is a hydrogen laser clock, which is a very, very precise atomic clock that can record the arrival times with extreme precision. So that we record each wave and put a time tag on it and record it on a hard drive. And then as if we've done this observation with a large telescope, we take these 2 hard drives, correlate the data, multiply it with each other, put it on top of each other, and that gives us a the signal as if we are able to observe that that distant black hole with the separation of or with the size of a telescope as if it was this big. Okay, this technique is called interferometry. But when the 2 elements are actually physically separated and there is no cable running through them, and you do this through a computer afterwards, it is called very long baseline interferometry. I'll stop for a question or 2. All good? The technique is fine. Okay, so what does this give you? Well, if you had only 2 telescopes, let's say this one, and you had 1 instant of time, you took 1 picture of your source. It would give you a particular 1 frequency, which is called a Fourier frequency, like as if you're hearing 1 note out of an entire musical score. And that would be actually pointing towards, this is the distance length between the 2, L between the 2 telescopes. So each telescope pair measures 1 Fourier component in the direction of projection of your telescopes onto the sky, okay, in that perpendicular direction. So we say, okay, out of this entire image or the frequencies that we need to make the image, we get this one and that, like it's symmetric one. That clearly, if you hear 1 note from a song, that's not a song. You don't know what it is, right? So what do? Well, you rely on the rotation of the Earth. So as the Earth rotates, you get different looks at your source. And then you make, oh, there is this pair and that pair and that pair. So any 2 telescopes gives you a new Fourier frequency. That's why we needed not just an Earth-sized separation, but we needed a full array to fill the Earth as much as possible and to get a different look at our source. It's like going to the doctor for a CAT scan or an MRI, and they take you in and the machine rotates around you to get a different look from. This is exactly the same thing, except we're not rotating the machine, we're waiting for the whole Earth to rotate to get these different frequencies. So this is the M87 data. Each pair of telescopes, it has a color on this image. And if you collect all of it and put it in one, forget about the azimuthal direction, as if the image can vary across, but you say, okay, what do I know about at different lengths? So you put that amplitude that you measure as a function of the separation between any 2 baselines. That's the baseline length, it's the spatial frequency. And all of our data gave us this nice ringing structure, okay? This ringing structure is a Bessel function, and it is the Fourier transform of a compact image. So an image that is extended like a Gaussian, when you take its Fourier transform, does not have this ringing structure, okay? First minimum, second minimum, etc. This is already a telltale sign that you have something small. Great. Okay, let's look at Sagittarius A stars. This is again all of the coverage between different telescopes. This is that ringing structure. And because it's a little bit closer compared to M87, I mean, it's closer, it's smaller, but the angular size is a little bit bigger. As you can see, we also have some data after that second minute. But you would say this and this look pretty similar, right? So that's when we knew that this experiment worked for both of the black holes. You can do one other thing very, very quickly, which is you say, okay, if this is a Bessel function, what is the relationship between the size of the source and this first minimum, maximum, second minimum? Well, the first minimum gives you the diameter of the source in microarc seconds. This is just because this is very close to 3 giga lambda. We scaled it to that. It basically says the source is 52 microarc seconds. We know the mass. We know general relativity's predictions. We've done all of that simulation library, right? And we know that it's a intrinsic characteristic of the black hole's gravity. So we can now do a test of, is this what you predicted? Okay, is this really the size? So I will get to that, but I want to tell you just a little bit more. It's very fun when math is, you do all of these complicated simulations, all of this complicated instrumentation, telescopes around the world, etc. And you get all of this data, and then it turns out to be something that's understandable with one simple mathematical relationship, and that's always extremely exciting to me. So let me show that to you a little bit more. I said here that there's a relationship between the diameter of the source and where this first minimum occurs. If you look at that visually, let's say that this is 50 microarc seconds as a reference, and you start out with a smaller source, okay? And this is the data that I showed you for M87. The Fourier transform of that orange circle is this green line. You don't need to be an astronomy or physics student to say that is not a good match to that data, right? This is really, really bad actually. Okay, what can I do? Well, since it's a circle, I can change its size. Okay, getting better, right? Now at least I got this first minimum right. And really at that point, it's 52 microarc seconds in diameter. Okay, but still you would say, I don't think I'm describing this data very well, right? What else can I do? Well, I said it's a Bessel function of a compact source with finite edges. So it's either a disk, like I've drawn it there, or it's a ring. Okay, that's the other thing that we can do. Okay, we're getting there. So now, not only do we know it's that size, but that it has that hole in the middle that we were looking for, that we were after. And then this, why is this not a good fit? Because this assumes like we have infinite resolution. Our array is limited to the Earth, so if you take into account the array resolution, then it's a. So you can do all sorts of fancy things, but at the very core of it, the result is simple. the result is that these data can be explained by nothing other than a ring. And the size of that ring is 52 microseconds, about 52 microseconds. So now you can say, fine, is that what you predicted, given what you know about the black hole and general relativity? I'm going to skip this. I was just going to say, that's a simple way of understanding it, but we have, of course, very fancy imaging algorithms, actually dividing the image into many, many pixels and assigning a different brightness to it and finding, okay, like, what is this actual image? If you use more of the information and that gives you the slight asymmetry between the east-west direction and north-south direction. One of them is fit by these data, the north-south direction is fit by these data, and that's because it's not a perfectly smooth, uniform ring. It has this Doppler asymmetry that I mentioned. Okay, so two black holes, two images, similar sizes, similar shapes, other than maybe a little bit where the brightness is distributed. There is that shadow in the center. There is a narrow ring of emission from the plasma, that hot swirling plasma that I described to you. And then there's that Doppler asymmetry. In this particular case, of course, what we're inferring is that the handedness of the swirling is this way. So the bottom is coming towards you, the top is going away from you, and the angular momentum axis is that way, which incidentally aligns with the jet of the black hole, which is a good confirmation that we're on the right track. Okay, so maybe in the next 10 or so minutes, I want to go a little bit deeper and go from these general considerations to how we actually made a measurement of whether general relativity is correct or not in this particular setting. So I'm going to stop, take questions, drink some water, and then spend 10 more minutes on general relativity.
The image you have shown, how you have chosen these two targets, actually entered one seems quite near to some limit. Will you have a new target there?
Yes, so with the existing telescope array, the Event Horizon Telescope Array, we've actually looked at about 8 targets. Some are a little dim, some are a little too small to be resolved, but what we were able to see is the jet structure. So most of them, just like M87, have jets. So we don't have any other images that resolve this horizon and the photon ring, but indeed, we have other publications from the collaboration where we looked at other targets and maybe resolved the inner structure of the jet, or some interesting thing about the black.
You have already looked at M21, but it's not good an image. Is that what we should understand?
It's not at this level. It's in. And 31, if I remember correctly, I think it's magnification rate is also different. So it would have been a good X-ray target, but it's not an ideal target at 1 minute. Thank you for that question.
I mean, you have exhausted all the targets. That's what it means.
We've exhausted all the targets that we can do from the Earth. I'm working on getting a project going to do this from space.
Moon?
Not moon. We've done some orbit optimization. You need to go above the geosynchronous orbits, but you don't have to go to those. So, we haven't published it yet, so it's, in the works, but, an ideal would be about 10 Earth radii for the tops and major axes.
Bir sonraki adımda daha iyi bir teknik bulursanız bu şeklin nasıl bir şey olacağını düşünüyorsunuz?
Daha iyi bir teknik derken, okay. So the question is, if we find a better technique, would these images change? We will still have to rely on interferometry. There is no way to get that kind of angular resolution without relying on interferometry. What are the things we can do for it to be a better technique? We can go to space, which we're looking into. You can change the wavelength even further. As you go to shorter wavelengths, the technique becomes more difficult, and you're also dealing with what the atmosphere allows to come through or not. The particular wavelength of observation, 1.3 millimeter, comes through our atmosphere pretty nicely. It gets absorbed by water moisture a little. But we've already started observing at 0.86 millimeters. That's going to improve the resolution and probe a different part of the accretion flow. So we're already doing that, and we don't have the data analyzed yet, but as the PhD would run those observations. But going to space, you're not limited by the atmosphere. So you could also go to other observing wavelengths and improve the technique. So we won't ever be able to move away from interferometry, but we can do it better in others. We'll see if we see something different. That's why you do this.
Just a quick comment, actually. But then, isn't this what the theory predicts?
Yeah.
The images, right? Yes, theoretically predicted, so why would you want to have something different? This is predicted and you actually found it, right? So,
Absolutely right.
and then there probably isn't a very, very different look into this anyway.
That's a good comment, but coming from being able to do it for only 2 sources to about 30